Okay, great. So it's my pleasure to welcome Swarat Chaudhuri. So Swarat is a professor at Rice University. He's actually currently on sabbatical here at ETH. So, so Swarat got his PhD at the University of Pennsylvania under Rajiv Allur, working on formal methods, automata theory, and he actually got the SIGPLAN Doctoral Dissertation Award for his work. Since then, since he graduated, he's been moving and working on topics in program analysis and synthesis. He's done very interesting work on program robustness. Very nice papers on Popo and other places. And over the last months or for the last few years, he's become more interested in also machine learning and statistical reasoning. So please go ahead.
Thanks very much. As Martin said, I'm now on sabbatical at ETH Zurich, and I'm loving it. Thank you. But when I'm not on sabbatical, sometimes I have very smart undergrad students show up at my office and ask me, what do you do for research? Right? So when they do that, I usually try to sell them on the dream of formal methods. And this usually includes phrases like careful program construction and clean abstractions and proofs and so on and so forth. But there is always this sinking feeling that even though I'm promising them the Taj Mahal, when they graduate and go into the software industry, the world that they'll see is a little bit more like a bazaar. And let's not knock the bazaar. It's a very exciting place. There are lots of applications, lots of codes, lots of APIs. Things move fast. But of course, things are also brittle, insecure, and reliability is a serious problem. So over the last couple of years, we started investigating these questions where I think one way of describing them is, can we find something redeeming in this vast bazaar of software that's out there? Okay? So the reality is that there is a lot of very rich information in all the code and all the documentation, all the forums that are out there in the world. And human programmers, they draw on this knowledge all the time when they, for example, read code from GitHub or go and check out posts on Stack Overflow. And this could include questions like this. Right, so the thesis of what I'm going to talk about here, and also what has been explored extensively by Martin and Veselin and others in their recent work, is that this sort of knowledge can be extracted using statistical techniques and used to guide program analysis and synthesis tools. And a lot of this talk will be about learning from large code repositories, what has recently been called big code, right? And the justification for that perhaps is captured by this plot, where you see the number of open source projects on GitHub. And as you can see, the number is growing like crazy, and at this point, there are almost 20 million active repositories on GitHub, right? And these programs actually contain a lot of information. They contain information about what real-world programs look like syntactically, but also because programs are entities with semantics, you can also imagine analyzing them and coming up with rich semantic information. And the question for us over here is, can we extract this knowledge that is hidden inside these big repositories and then do something fruitful with them? Okay, so what are these fruitful things? Right, so I think that the answer has to come back to a couple of things about formal methods that are perhaps not that reasonable. And the most important thing over here is the fact that formal methods rely on formal specifications. And the reality is that formal specifications are not easy to write, right? Especially for the typical programmer. And there's this assumption over here, which is that the user knows everything that they want and can express this succinctly in some sort of a mathematical formalism, which is perhaps often an unreasonable expectation. Now, there is a long history of work in software engineering, primarily, which is on learning specifications, right? And one insight over here is that what we think of as bugs are often anomalous program behaviors. And then you can think of a specification that is a definition of what is not a bug, right, as some sort of a commonplace pattern that appears across large numbers of program behaviors. And this insight has led to people studying methods for learning specifications automatically. And here, what we are trying to do, what we are going to talk about, part of that is going to be about how do you learn specifications from behaviors generated from large bodies of code on the internet. And another dimension of this is that in formal methods, you are typically looking for solutions to very hard algorithmic problems. So these are not things for which you can get a polynomial time worst case solution, typically. Right? So you need heuristics, but where do you get these heuristics? The assumption typically is that the designer of the formal system is going to have enough insight about the domain where the tool is going to be applied, and they're going to come up with these very nice heuristics. And let's just say that this is an expectation of knowledge, which is also not always true. In fact, often this is not true from my experience of building some of these systems. And one idea then is that perhaps if you could look at a lot of knowledge about how programs actually look like, how proofs actually look like, then perhaps you could learn from there some information that could be used to guide the search for proofs and programs or test cases, whatever you have for your particular application. And this is an idea that's relatively recent, but this is also explored in some of Vesselin's work or some work from MIT and also in some of the work that I'm going to talk about here. Okay, so operationally, what all of this is going to mean is that we are going to talk about coming up with statistical models for learning specifications and heuristics from large corpora of code, and more generally, as we will see later, also other forms of data. And secondly, we will talk about algorithms from program analysis and synthesis that target these sorts of learned specifications and use these sorts of learned heuristics. And the challenges here are going to be on both sides. So the statistical models that we'll talk about, these are going to be often models for complex structures like trees and in some of our more recent work, graphs, right? Because programs are very complex objects. So there is some innovation possible there on the machine learning front. But there is also this question of how to successfully combine these sorts of statistical models with programming tools. And I'll give 2 examples of that. Okay, and just to be clear, we are working on this for the last few years, but there are also other people. So I see this really as a movement, and there is a lot of interesting work going on. So if you check back on this area next year, you'll probably see even more interesting results. So now onto the concrete instantiations of these ideas that I'll talk about. So one idea would be of bug finding using these sorts of learned specifications. And if you want to know more about this, we published a paper on this topic at FSC this year. And here the high-level idea is that you want to do debugging without specifications for, in particular, APIs. And we are going to learn a wide range of specifications for how to use APIs from a large code corpus, and then we'll use that to quantify how buggy or anomalous a program is. And then the second instantiation is in the context of synthesis. So we have this new method for synthesis with ambiguous specifications. Typically in synthesis, you think of defining a formal specification in some sort of a logic and then trying to find a program that fits that. Here, our goal would be to give very, very partial insight. So for example, just some of the API calls or some of the types that the program uses, or some natural language description of what the program is supposed to do. And from there, we'll somehow extract the true specification of the programming task and also come up with synthesis algorithms that benefit from this knowledge. Okay, so to start with, let's talk about bug finding. I'll start by just going back to the classical definition of correctness analysis in formal methods, and then we'll try to generalize this idea probabilistically, and then we'll see that we get something like what we do. So in classical correctness analysis, a program behavior is often viewed as a trace, a sequence of program actions. right? So it could be, for example, a sequence of API calls. A program is modeled as a set of behaviors. And a specification is also modeled as a set. It's a set of correct behaviors. And then when you're thinking about correctness analysis, you ask this set theoretic question. The set of behaviors that the program generates, is this contained in the set of behaviors that is correct, right? And there is a lot of work on this, in model checking, in program analysis, so on and so forth. Now, here, what I'm talking about is generalizing this view probabilistically. So rather than talking about behaviors and specifications as deterministic objects, we are going to think of them as random variables. Okay, so we are going to have these 3 different random variables, which I'll call x, y, and z. So x is about just what a program looks like. Okay, so this is going to be a syntactic abstraction of programs. And there would be a distribution on this. And this distribution, you can think of it intuitively as capturing the frequency of different sorts of syntactic forms in the wild. We'll have a variable for behavior. And this is, again, going to be a sequence of program actions, except it's a random variable ranging over that data type, right? And again, the distribution of this variable, you can think of it as capturing the frequency of different sorts of behaviors that appear when you execute programs. And then finally, the specification, we don't really have it, right? So we are going to think of it as a random variable that you cannot see. You can only see other kinds of random variables, like you can see examples of what programs do, you can see examples of what programs look like, but you don't really know the specification that's behind this. So we are going to see it as a latent program variable that controls both what a program looks like and also what a program does. And we are going to make, for technical reasons, this assumption that this specification Z is really it captures the entirety of the intent behind the program. And so the way a program looks like, that's this X, that depends on this Z. And the way the program behaves, that's Y, also depends on Z. Okay, but the Z is hidden. You can only look at X and Y, and you can infer Z from that. And then, because these are random variables, we'll have to make some assumptions about the distributions on them. So we'll assume that for any given program, the semantics of the program is given by a distribution. So this is, again, a departure from the set theoretic point of view, that you're not thinking of the behavior of a program given by a set of behaviors. Here you're thinking of it as a distribution over the behaviors. And to get an understanding of what this distribution looks like, you could imagine running the program on real-world inputs and just seeing what sort of behavior shows up, right? But here we are going to do static analysis, so we won't be able to do that. We'll just assume a certain distribution over these Ys. So then what does learning look like here? Well, so ahead of time, you look at GitHub, you generate a whole bunch of pairs of this form. These pairs include the shape of a program, right, the X's, and the corresponding Ys, right? What does this program do when executed? And you generate a ton of pairs, and from there, using statistical techniques, you learn a joint distribution over these 3 variables. And then, what do we mean by correctness analysis? Okay, so you're given a program, and you're asked, is this thing correct? So we don't have a specification. But what we could do is that we could compare these 2 distributions. One distribution tells me, what does this program do, right? So this is that this P of Y that I talked about earlier. And the other one is a conditional distribution of P of Y given XF. So XF is basically what this particular program looks like, okay? So you are consulting this knowledge base that you have learned from data, and you are querying it that I'm given this particular value of X, right? What is the behavior I should expect from a program that looks like this? And if these 2 distributions are too far apart, right, if they have a high statistical distance, then you conclude that your current program is anomalous, right? So the distribution of behaviors that it generates is very different from the distribution of programs over behaviors that programs that look like it are supposed to generate. And You can define the statistical distance in a bunch of different ways. We considered this classic distance measure called KL divergence, and the exact expression for that is here. It's a sum. The details don't really matter for us. What matters is that if the distance is high, then this program is going to be anomalous. So then this is what our workflow looks like operationally. So you're given a big corpus. So from this corpus, using this probabilistic behavior model, right, you generate a whole bunch of behaviors. So you have these pairs, X and Y. And then you do some large-scale training, and then you learn a joint distribution over this X and Y and Z. And then at analysis time, you're given a particular program, F. So you also apply the behavior model to come up with a distribution over what this program does, and also you have the information about what this program looks like, right? That's your XF. So then you get these two distributions. One of them is P of Y given XF, and the other one is what you had, the behavior model, and then you just compute the KL divergence between these two things. So let me try to make this all a little bit more tangible by using a concrete example. So here we have an Android app, and it's popped up this dialog box, which cannot be closed. Or you can close it, but then you have to press Android's back button. You have to go outside the app, right? So the app doesn't really support any way of closing this box, and that, I think most of us would agree, is a bug. So why does this happen? If you look at the code for this app, it turns out that there is a certain combination of conditions where you create this dialog box, and then you don't actually put any other content in it. You just show the dialog box, right? And this is not something that would show up in normal execution. It's something that, in fact, our static analysis tool found, and then we were able to come up with a concrete example of this happening, and then we reported it to the software developer, and they fixed it. Okay, so for this particular program, what is our definition of this probability distribution over behaviors, and also more generally, what sort of concrete statistical models that we use for doing all this analysis? That's what I'm going to talk about next. As I said earlier, what you could do, conceivably, is that you could take an app and you could run it on a whole bunch of realistic inputs. Unfortunately, that's often not practical because you don't have the right inputs, especially for things like Android apps. So we just modeled it statically in the form of a so-called generative probabilistic automaton. So you can think of this as a probabilistic generalization of finite automata. You have labels, just like in finite automata, but now you have these probabilistic weights on transitions as well. And this sort of a model can be seen as generating a probability distribution over words, right? Words that are in the language of the automaton. So that's going to be our notion of this behavior model. And this is something that we get out of real programs using some very lightweight static analysis. So then the question is, what do we do for learning? Right, so we have to learn this joint distribution P of X, Y, Z, right, given examples of X and Y. So here we use, first of all, you could do this in many different ways. We use a particular combination of a topic model and also something called a topic condition recurrent neural network. I'm just going to give you an intuition of what this topic model is. So it's going to capture the part of the distribution that includes X and Z, right? So it's, if you look at the distribution function P of X, Y, Z, by your assumptions, it turns out you can factorize it in this way. And I'll just talk about the first part in the next couple of slides, very briefly. So a topic model, in particular the topic model that we use, it looks like this. So you have a bag of symbols that you're looking at. Okay, so this can come from some sort of a document. And you are modeling this bag of symbols as a probability distribution over topics. So for example, a particular bag of symbols, a particular document, if you will, it can be, say, 50% dog-related, 30% cat-related, and then 20% other, right? And then each of these topics, this is viewed as a distribution over symbol. So for example, the dog-related topic can be a distribution that says, with high probability woof, with high probability bark, with low probability meow. So for us, these symbols are actually API calls. So what we are doing then is this in this XF, we are creating this bag abstraction of programs. We are just generating the set of tokens, right? And then we are just throwing this topic model at it. And the specification is actually this latent variable of the topic model, which is this topic distribution, right? And these topic distributions, they represent different ways of combining different APIs or even distinct ways of using the same API. And then that's what we have, okay? And then actually, for the other part, if you look at this, so this is talking about P of y given z. So y is a behavior, so it's a sequence, right? And z is, as I said, it's a topic distribution, right? So there it turns out that there is a kind of recurrent neural network that is a neural network that generates sequences, right, which can be conditioned on a topic vector. So that's what we were using there. So just to give you an idea of what this looks like in the context of programs, so if you take a bunch of programs and then throw them at this topic model, you're going to find that different topics emerge. And these are actually there is a correspondence between these topics and different APIs, it turns out. And also, in some cases, different patterns of using an API. So here, for example, I have listed some of the topics. So here you see that these API calls are clustered together. So you have, set positive button, set negative button, set message. So you see that these are about doing dialog boxes, right, or other kinds of visual widgets. Whereas in some other cases, it might be about handling sockets, or in some cases, it might be about some other kind of structure that these Android programs manipulate. Okay, so that is our statistical learning, and you have to trust me that there is an easy way of getting back this conditional distribution out of that. So now, what's the final step? Well, it's this computation of the KL divergence, right? So you are given these two distributions, and you want to compute the distance between them. So as I was telling you earlier, this distance is actually, you can view it as a sum. So it's a sum over all paths of the automaton, it turns out. Okay? So there are folks in quantitative verification who have looked at some of these quantitative questions over automata, right? How do you sum weights along paths, across paths, and so on? So for us, we do something very simple, which is that we sample a whole bunch of these paths, and then we compute the terms of this sum for those particular paths, and then that's how we estimate this distance measure. Okay, so that completes the picture. So then let's go back to the example and just see, yeah. Yeah.
Make sure that, so the PFY,
yeah.
You get the automata, the probabilities. Can you say a bit more how you get the numbers?
So those numbers it's just some execution model which is fixed. So we have just, and in the experiments, we just fix the numbers to uniform. Yeah. Okay, so now going back to this example, so it turns out, perhaps not entirely surprisingly, that this buggy path that you get, it gets a very low probability in the statistical model capturing how things are in the world. And then this leads to a high anomaly score for the entire program. And then if you delete this path, then it turns out that the anomaly score goes down, right? So we implemented this and trained this on a large corpus, and we found a whole bunch of interesting bugs, things that you wouldn't normally express using a formal logic, right? So things like unusual button text. So we found this situation where there was a button and there was a comment that was left as a placeholder, and somehow it became the text of the button, right? And then other things like dialogue displayed without message. In some cases, there were pretty serious errors, like there is a crypto API call that was made without specifying the encryption mode, and it turned out that defaulted to a weak form of encryption. Right? This is, again, one of those things where you have all these APIs doing weird things, no formal specifications, and so it's easy to make serious errors. And this doesn't go certainly as far as real formal verification, but this can, for a completely unsupervised method, I think this can give you some interesting insights. So I'm actually not going to give you any experimental numbers in the interest of time. You can look at the paper, and if you have questions, you can ask me later. Bottom line here is that the method works reasonably well. We didn't invest a lot of time in engineering, but it turns out that we still get about 20% false positive rates, which is not amazing, but it's pretty decent. Okay, so now I'm going to switch to the other topic of synthesis, but if there are any questions, I'm happy to take them. Yeah? So we actually had to manually go in and check the bugs that were reported on a small set of APIs, because that's not possible to do for all the APIs that are there in the Android namespace. But for those 3 or 4 APIs, my postdoc actually went in and manually checked all the reports that had anomaly scores above a certain threshold. And then, of course, there is some subjectivity here. He had to classify things as bugs or not bugs, right? What a normal person would consider as a bug. Anything else? Yeah?
So just a quick question. So the bugs the reports that were on the slide, are these mostly like relational in the sense more like type state, like on sequences, or it's more like this API should not be called with these parameters, or it's more like this API should not be called after this API?
So it's all of the above. So we have examples of cases where the parameters were off. So one example of that is that you're calling a crypto method with the wrong encryption mode. But there were also some temporal properties, such as you shouldn't close. You should always remember to close this socket, right? You shouldn't do certain things with this socket open. And there were also a couple of interesting properties that related multiple APIs, actually. So it wasn't just type state. Okay, so let me now switch gears and move on to synthesis. So here again, I'll start with this classical view of what synthesis is, and that's that there is this thing called a specification, which is a logical constraint or a set of program behaviors. So it could be given to you as a set of traces or a set of input-output examples, and so on and so forth, right? But the point is that it's a very formal, rigid artifact. And then you are modeling the program as, again, as before, a set of behaviors, and what you're trying to do is to find a program, right, that satisfies the behaviors that the user has given you. So this is well and good, but if you think of it, a lot of places where you would conceivably use synthesis, there would be this essential role of ambiguity. A user who's trying to get a program out of a programming tool doesn't necessarily know to write a full constraint of about what the program does. And yes, they can give some behaviors, right? That is interesting enough. But in many cases, they will have sort of a fuzzy idea about what's going on, and it wouldn't necessarily be a hard requirement. It would only be some evidence, if you will, towards what sort of programs they want. So here in this work, we took a probabilistic view towards this question of synthesis. And so the vision is something like what you see here. So there's a user who's dreaming about this idealized program, okay? And they give some very ambiguous evidence to the synthesizer, saying that these are some clues towards what kind of program I want, okay? But in addition, they might also give some hard constraints which you want to respect, and that's fine, right? That's the more traditional part. So this synthesizer, unlike the traditional synthesizer, would be equipped with this statistical model, so that will have been trained on data, and from there, it will basically have built a model of how to design programs, right? So what's the relationship between different kinds of specs that you see in the world and the corresponding programs that match them? And based on this model, it's going to come back with some guesses about, okay, this is what you said you want. These are some of the possible programs that fit your needs. And these programs we want to ensure should satisfy some correctness requirements, so that's why we have this logical requirement phi. So what are some examples of this evidence, right? So here are a few. You could, for example, just give a few API calls or types that the program uses, not giving anything else. Now, you can imagine if you just ask a synthesizer which doesn't have such a model, right? Give me a program that does readline. Well, okay, here is a program that uses readline. It's just readline, right? That's the one-line program that matches this. But that program is obviously nonsensical because that's not what you want when you are a programmer, you're trying to read lines from a file or something else, and you are telling the system that, hey, give me a program that uses readline. But it could also include other things like IO examples, natural language, description, so on and so forth. So I'm going to give you a very, very quick demo of this. And here is oh, what just happened? I switched to the browser. Does that, to the what? Oh, I see. Okay. Except now I don't see. I can't, oh, except I don't even have a, oh, okay. All right, so what you see over here is an example of what we call a draft that people would write in our context. So you have a program which contains very little information. There's a method called read. It's taking in an argument called, it's a string, and it's called file. And then the user is just specifying that the program that they want uses the API called readline, and it uses the type file reader. Okay? So now if you, wait, this is, okay. So now I'm just invoking this, and by the way, this is running on a pretty slow machine, so it's going to take a little while, but here's what we get out of here. Okay, so here, what we are seeing is that even though you gave this very limited amount of information that you are using a certain API call and a certain type, the system has actually been able to come back with a pretty detailed structure of this program. So what's going on over here? So this program, as you see, it takes in the file and it opens a file reader. It opens a buffered reader. It reads the buffered reader line by line, right, until it is empty. And then it even catches exceptions, okay? So why did that work this way? And the reason is that, again, if you look at the corpus of programs that use these two particular things, that read from a file and that also use calls to readline, there are almost no programs that just read a single line from a file, right? People typically read files line by line when they're using readline. And that's why there is this structure that came out of the corpus, and then our synthesizer worked with it, right? So I could play with this. I could show you more variations on this. So actually, this is a probabilistic method, so you would be, if you just went and tried some of the other examples, so if you navigated this bar, these arrows, so you could get some of these other examples. So here, we see that the reader is actually being closed, which you would think is the right behavior, but often people don't do it. So our statistical method, because it doesn't really know any better, it just, in the first result, it didn't have that closed result, right? And you could go with this, and you will see that the next result would, for example, it's going to call a file reader, but it's going to create a new file object out of the string file. So that's a different way of creating that object. Okay, so I wouldn't recommend that you go to this URL because we have a slow machine, but we are creating an Amazon backend that's going to be online pretty soon, and then this will be public, and you can play with that. Okay, so very briefly, what this technique is based on. So the first and most important point here is that learning at the level of just syntax doesn't actually work, right? And the reason for that is that there is just too much variation across programs that are meaningless, right? So you may have two different programs that are reordered, slightly reordered on some of the low-level assignments and so on, but they are doing basically the same thing so far as the API calls are concerned, right? Or some of the reusable facets of programs are concerned. So that's why what we do over here is that we learn at the level of abstractions. So we create these abstractions or sketches out of programs, and then we learn to associate these abstractions with these sorts of labels that appear in the programs, right? So for example, you could associate, combinations of read line and file reader would be associated with a certain kind of tree structure for the program, right? And how to do that, I can go into more details, but how much time do we have?
10 minutes.
Okay, 10 minutes. So maybe I can tell you a little bit then. So we have, again, this probabilistic view that there are these three random variables. So we have this thing called y now, which is, again, y is the output, x is the input. So y is now a sketch of the program, right? So it's a tree-structured entity, a tree-structured abstraction of the program. And the evidence is the kind of things that the user is likely to enter during synthesis time. So for example, the name of a type or a name of an API call. And then, again, like in the previous case, we have this hidden variable that is controlling both x and y, and that's something that we want to infer from what the user says. So like in the last case, what we are going to do is the user is going to give us this x, and we are going to come up with a model for this z, right? And that you can think of as, what does the user really mean, right? What's the real intent behind the program, behind the specification? And then from there, we'll have enough information to go and generate this y, which is a sketch of the program, right? And once you have a sketch, then you have all these methods, informal methods, that can tell you how to go from a sketch to a program that satisfies a requirement. So just to give you a very, very high-level idea of what is the level of abstraction at which we are learning things, so we are essentially keeping the high-level syntax of the program, so the structure of ifs and whiles and try catches and so on. But we are abstracting away all the low-level variable names, all the low-level assignments and all of those things, right? So we are only recording some actions of the program, which are these API calls. And naturally, we want to keep only facets of those API calls that generalize across programs. So we are only keeping track of what types were used as arguments to those API calls and nothing else, right? So then we learn over these sorts of structures, and then what happens is that during synthesis, the user gives you some evidence X. So you have this statistical model that's actually for us learned using a neural architecture, right? And then from there, you get back this distribution over Y is given X, sketches that are likely to match this given evidence. And then we have this step where we just use all of these techniques from program synthesis to start with the sketch and concretize it into a program that satisfies some additional logical requirement. So I'll end with just a couple of slides about some of the things that we are doing now, extending this work on synthesis. And that's something like this. So in this work that I showed you, so here the role of learning is to basically give you some high-level story about what your ultimate program looks like. So let's say that you are thinking about a robot programmer, a synthesizer, which is just going and generating programs. And the way these things work often, in fact, this is something we have explored in some of our recent work, is that you follow this top-down so-called refinement-based strategy. So what that means is that you start with zero knowledge about the target program, and then you add a little bit of code, right? And then you still have an incomplete program. And then you add some more code, and add some more code, and add some more code. And so you're basically getting this tree structure, right? At the leaves of which are complete programs, and the root of which is basically zero. You know nothing about this program. That's your starting point. So this is your robot programmer. There are other algorithms too, but let's think of this as a concrete synthesizer, right? So if you think of this sketch-based approach, so what it's really telling you is that, okay, and by the way, so these lambdas we originally did it in the context of a functional language. You can safely ignore all of this here. So you can think of it as, this is an intermediate node in the search tree. There is some code, but there is also a hole that you're trying to fill with more stuff. Okay, so this approach that I just showed you, you can think of it as doing the following. So you are at this point where you have a choice between, adding API call A or adding API call B, and you have a probability distribution that tells you that, okay, A is much more likely at this point than B, all right? So this is what somebody doing machine learning would call supervised learning. So you have supervision, you have a label, right? That's and you have or you have a bunch of labels, right? A bunch of API calls to fill in at this point, and you're making a decision about which one, right? Based on some probability distribution that's available to you. But one very interesting situation, which is what appears in more traditional synthesis, is that there is some sort of a constraint, some sort of a goal that you want to satisfy, okay? But this goal is not going to be, you don't know anything about that goal at this point. That's something that's going to show up in the very long term, right? You may make some decisions now, you won't know what it means until much later down the search tree. And that's the story of SAT solving, that's the story of this sort of logic-based synthesis, all of this stuff, right? So what I have shown you doesn't quite apply to that. But there is still this interesting question, right? So imagine that you collected a lot of data about how SAT solvers actually work or how program synthesizers actually work, right, for us. And you collected information about, okay, at this point, if I did this, then things didn't work out at the end. Or if at this point I took this other strategy, then things did work out for me at the end. So if you had information like this, perhaps you could learn from that, and you can even use that to speed up traditional formal methods like traditional program synthesis, program verification, all of this stuff. And that's what we are exploring right now. So the particular question is that you are looking at this program synthesis problem as defined traditionally, but you want to learn distributions over how to refine, right? Like how to go from a certain point in the node to the children, right? Which one to pick. And also, let's say that you are following this search and at some point you fail, right? Some point you find that, okay, things don't make logical sense, backtrack. Where do we backtrack, right? So normally the way to go is that you just go back one step, but there doesn't have to be any particular reason for doing that. You could backtrack way back in the search tree, right? And this is something that's actually followed in real-world SAT solvers. These heuristics are very important. So the questions we're asking is that, can you learn from experience to figure out what strategies are likely to be profitable in different kinds of problem instances? And here, the natural framework to use is what's called reinforcement learning. Many of you may have heard this term. This is something that's very hot in machine learning right now. Companies like DeepMind are basically based on reinforcement learning. And the most prominent successes have been in these game-playing problems, like, for example, playing Go or playing video games like Atari games and so on. So the question here is that you're not going to get a reward from your actions now, but there is going to be a time-delayed reward. Eventually, you will figure out that what you did paid off or didn't pay off. Could you somehow learn from this sort of information and get something reusable that can be used to speed up synthesis, verification, SAT solving, any number of problems like that? And it turns out that there is some past work in the machine learning community from back in the day. And we are reading those papers, and we have some initial results, and things look actually very promising. So with that, I'll end, but I'll just talk very briefly about the implications of this. Number one, I think the biggest takeaway is that I think uncertainty is a big deal. Uncertainty in our knowledge about what a programmer wants when they are invoking a programming tool. Uncertainty about what sort of strategies tend to work in what sort of problems. And this uncertainty has always been this hidden secret of formal methods. I think we should bring it out in the forefront and tackle it as a first-class problem. And secondly, one way to combat this uncertainty is to learn, right? Collect data of all sorts from big code, but also, as I showed at the very end, data about how these solvers actually work, more generally how programming tools work, what kind of user reaction do you get for different kinds of answers, and learn from there. And that can be a way of dealing with this uncertainty. Yes, things are never going to be perfect, but we will know that users tend to prefer these results more than some others, so these kinds of strategies are more likely to work than this other kind. And finally, even though I have been talking about statistical learning primarily, we have to always remember that logic very much matters in this context, right? Because at the end of the day, we are not talking about images of dogs and cats. We are talking about programs, we are talking about proofs where certain hard logical constraints need to be respected, right? And so the statistical learning can get you close, it can give you some heuristics, right? But it cannot go all the way. And so a combination of statistical and logical methods are therefore absolutely critical. And with that, I'll end the talk. Thank you.
Thanks. Okay, questions? Yes.
So this is about the first part of the talk.
Yeah.
So basically, there are anything that's less seen in the corpus of behaviors would be flagged as a bug. So what will happen in cases where the majority of the behaviors are actually wrong that you see?
Yeah, so there's an assumption here that democracy works, that the corpus is of reasonable quality and the behaviors are actually, somewhat correct.
Okay. So maybe, because we're thinking of the case of crypto APIs, which are actually, the majority of those are wrong on GitHub.
So here what we found, though, is that we were able to give a high anomaly score to that particular behavior, right? Now, it's certainly true that there may be other things, other bugs that are so widespread that the system would just think that, this is the normal. So there you can't really do all that much using our method. So one has to complement this sort of statistical unsupervised approach with maybe something more supervised where a human goes in and flags some behaviors as buggy, and then you look for similar bugs.
Okay, more questions? Yeah.
So for the synthesis approach, in the concretized programs that you generate, how much do those differ from specific example you may have in the source space? So for example, I'm wondering if there would be any value of actually reporting a concrete example of how someone else may have implemented this versus the programs that you're actually generating as completions.
So is a fair way of rephrasing what you said is that if we took a search approach, that we just got back some programs from the corpus and compared that with this approach, then would there be a difference? Yeah, so we have some experimental data in the paper that shows that you can, in fact, generalize to some tasks that you haven't seen at training time, right? So some combinations of API calls and methods that weren't seen at training time. It's not quite modular. So yeah, at the end of the day, it's a neural net that's putting together things. So we have some control in the form of, in the requirement of type safety, right? That the composition has to be type safe, but the Java type system is pretty weak, so it doesn't necessarily, guarantee that the programs will always be sensible. But what we do find is that sometimes you do get sensible programs that are obtained by composing two sorts of APIs that weren't seen in the exact same form in the corpus.
All right. In this order, it's easier.
So in the last part, you had this idea of using reinforcement learning to learn how to synthesize or to solve. So I like the approach of reinforcement learning, but there are other approaches in natural language processing where they use other deep neural synthesis methods and then something like beam search, which are more computationally tractable than reinforcement learning. So have you looked into those, or is the reason why you're going for reinforcement learning directly instead of those?
So the issue is that, so in contrast to what I showed in just before that part of the talk, right? Here you have this goal that's a logical constraint, right? That's a departure from what you normally see in NLP because here you have a hard requirement, right? And so the problem with hard requirements is that you cannot define satisfaction on just partial programs. So you have to go all the way down this tree, right, to the end or maybe close to the very end to definitively know that, no, you're not going to satisfy the goals that you have. But that doesn't happen right away. That happens later, right? So there is this time delay, which is the essence of reinforcement learning.
Thanks.
When you're using reinforcement learning, what are the rewards, particularly the temporal difference ones, please?
Yeah, so at this point, we are just working with a very simple model. So you have a very simple class of specifications, constraints, right? And you are getting a positive reward if you satisfy it, and no reward if you do not satisfy it, right? And then I think there are a couple of other heuristically chosen things too, but that's about it. So we are at the very early stages of that exploration, but the results seem to be that if you just look at the state-of-the-art synthesizers that are not using any smart heuristic, just using something dumb or just exhaustively searching, you can already do better than that with something very, very simple, a very simple reward function. But the hope is that as your reward functions get more fancy, you have better representations of policies in the form of deep neural nets or other things, we would be we would have huge gains over traditional synthesis.
Would it help if the programmer would give you a skeleton of the program, so a buggy version, an incomplete and buggy version of what he wants to do, like writing bad pseudocode, like for all instances and so on?
Yeah, one of my students is actually looking at that. So the idea being that you just write some pseudocode, right? And now when you are doing search, you basically prioritize based on the distance from that pseudocode. Yeah, so some people in my group are looking at that problem too. But yeah, that makes sense.
Okay, I think any other questions or take them offline, I think, right? Okay, great. So let's thank Swarat again.